Okay, everyone, welcome to our penultimate class. I want to start with a question that, apropos the regularity criterion I gave last time. Nice, simple question to think about in its own right. Suppose we have a triangle in the plane and we focus our attention on one of its vertices. Then you might imagine a Brownian path starting at this point to go like this, but you also might imagine that it goes over like this and enters the triangle with finite probability. But even worse, you might imagine that the path, not only does it enter T once, but it enters it infinitely often and for arbitrarily small times. So here's three scenarios. The path doesn't enter the triangle at all, even though it starts at the edge of the triangle. It enters it at some positive time, but there's a significant portion of time where it doesn't enter the triangle at all, or it enters the triangle infinitely often and for arbitrarily small time. So which of these three properties obtain, or do they each obtain with different probabilities? Well, the answer is, the theorem is that almost surely, we take this Brownian path started at P, I'll use the notion BP for that. BP of T is in the triangle T for a sequence of times Tn tending to 0. Now, this is not really too hard to believe. So in fact, what a Brownian, if we forget the triangle T for the moment, what a Brownian path tends to do is it spirals back and forth an arbitrarily large amount of times around P in both directions. And indeed, you can think of the variable theta of BP as itself doing a random walk in the circle, where by theta I mean the argument of this angle from P to BP of T. Because the argument is a harmonic function, this is itself doing a random walk. Alternatively, you could think of the complex plane minus P as looking like an infinite cylinder with P down at one end, and then you have a random walk coming up the infinite cylinder. And the probability that this random walk doesn't wrap around the cylinder infinitely often is 0. Okay, so that's how Brownian paths behave near near the vertex of a triangle. And as a corollary of that, we have that if you have a domain omega and you have a point in the boundary of the domain which can be touched by a triangle from the outside, then this is a regular boundary point. So that's the theorem that I announced last time, and I'm just sketching. I'm sketching the proof of it. But how rigorously would you prove this property that I just announced here, that almost surely you hit the triangle in arbitrarily small time? So for the proof, there's a neat argument which goes like this. Suppose not. Then, if we let tau be the random variable defined by the least value of t, such that BP of t is in the triangle, then the probability that you have to wait a positive time before you enter the triangle is equal to 1. This event is a 0-1 event. So either tau is equal to 0, in which case there is a sequence like this. This should be the inf of the tau greater than 0. Or tau has to be positive. So that's this alternative. You have to wait a positive amount of time. before you re-enter the triangle. So if the theorem were false, then with probability 1, you would have to wait a positive amount of time, possibly infinite. We just wouldn't be in this case. But now you can do the following neat thing. You can apply, let's call this triangle T1 and call this time tau1. So the probability that you have to wait before you enter this triangle, wait some positive time, that happens almost surely that you have to wait. And now you draw another triangle, T2. And that's exactly similar to T1, but it's been rotated. And the probability for T2 is the same as the probability for T1. So they must both be positive because Brownian motion's rotation invariant. And you put another copy, and another copy, and another copy. And eventually, with finitely many triangles, you cover a neighborhood of the origin. So then you get the probability that Ti is greater than 0, this being the probability, the amount of time you have to wait to enter the triangle Ti, all of those are positive for I equals 1 to n. And so if you take the minimum of the Ti's, this is positive, almost surely. And now suppose we take a time which is less than this positive time. Now what does that mean for that to be less than Ti? It means the Brownian path hasn't entered the ith triangle. So it's not in the first triangle, it's not in the second triangle, it's not in any of these triangles. So it means that we have, for all t sufficiently small, P of t is out here, because it's outside of all of the triangles. So it somehow jumped over all of the triangles at once, which of course contradicts the fact that Brownian motion is continuous. So that's a nice argument that shows that a Brownian path started at the vertex of a triangle, enters the triangle for arbitrarily small time, and that implies that these are regular boundary points. And so let me remind you what the point of that is. The point is that regular boundary points are those where, when we solve the Dirichlet problem, we know that the harmonic function we get is a continuous extension of the boundary values at that point. So let me just restate that theorem. Solving the Dirichlet problem. If f from the boundary of omega to r is continuous and omega bar is compact, then if we let f of z be the expected value of a random walk starting at z of the value of f at b sub z, well, I guess that's implicit here, at b of tau, then this is harmonic, and f of zn tends to f of p whenever zn tends to p, and this is a regular point in the boundary domain. So as a corollary, if all of the boundary points are regular, then this harmonic function solves the Dirichlet problem. So let me again just draw a picture to explain what's happening here. It's really a very beautiful aspect of Brownian motion that we have subdomain omega, and we have some function f on its boundary. And the way to compute the harmonic extension of this function at a point z is to let a Brownian path go over here, and it will hit somewhere on the boundary at time tau. So this is b of tau. Tau is the first moment that it hits the boundary. But different paths will hit at different points. So the expected value of f when the Brownian path exits the domain is a random variable. It's a way of sampling the points in the boundary of the domain. And it samples them in just the way that's necessary that that kind of averaging procedure leads to a harmonic function. So if you like, Brownian motion allows us to define for any domain the standard averaging procedure we would use to find the value of a harmonic function at the center of a circle. Okay, so with this in mind, let me just make two remarks on topics we've discussed from the point of view of the Riemann mapping, harmonic functions, several times that now have a simple probabilistic interpretation. So this is not anything but a change of language, but I think it really improves one's intuition for what these quantities measure. And the quantities I'm interested in are harmonic measure and the equilibrium measure. So a long time ago, we talked about harmonic measure without ever mentioning random walks. And it has something to do with describing the size of some set A in the boundary of a region, and especially how big this set appears from the point of view of a point Z in the interior. So technically, what we did was we took the harmonic function that was 1 here and 0 here. So we had to be able to solve the Dirichlet problem. And then we looked at the value of that harmonic function at Z. That was the definition of the harmonic measure of A. And of course, it was between 0 and 1 because the boundary values are between 0 and 1. But now we have a very simple and intuitive interpretation of what this probability is, because we know how to construct that harmonic function. Namely, the harmonic measure of A is just the probability that a Brownian path will land in A when it first reaches the boundary of the region. So omega, what we used to call omega Z, capital omega A, can now be described as nothing more than the probability that a Brownian path starting at Z lands in A when it first exits omega. So that is the meaning of harmonic measure. And now many of the properties of harmonic measure are just intuitively obvious. For example, if we make A bigger, then of course, the harmonic measure gets bigger. So that was something we proved using the maximum principle, but now it's just obvious because the event that you land in A is easier to achieve. And there's another aspect of harmonic measure that maybe wasn't quite as obvious. What happens when you make the domain bigger? What happens to the harmonic measure? Does it go up or down when you make the domain omega bigger?
Goes up.
It goes up. And you might say, why does it go up? And there's an argument with the maximum principle that it goes up, but that's rigorous. But here's really why it goes up. It used to be there were paths that would land here and then they'd be done. They would have hit the boundary of omega. But now, if you push the boundary out a little bit, there's a positive probability that that path turns around, comes back, and lands in A. So you've allowed the paths to survive longer. And the longer they survive, the more chance they have of reaching A. So those monotonicity properties are kind of self-evident when you interpret harmonic measure in this way. That's a kind of qualitative virtue of this point of view. There's also a quantitative virtue, which is this. Suppose we have a long rectangle, and A is this end of the rectangle. And in fact, maybe it's an infinitely long rectangle. And we pick a point Z here. And we ask, what's the harmonic measure of A? And Z is at distance, let's say R. from 1. Now, R is bigger than 1. We say, what's the harmonic measure in this domain of A? And maybe Z is on the midline, so this quantity only depends on R. Well, let's think about what a Brownian path does as it tries to reach A. So first, it has a 50% chance of just going in this direction and landing at the reflection of A here. So the harmonic measure of A is certainly less than 1/2. But imagine a Brownian path that's trying to reach A. So it moves a certain distance towards A, but now it has a definite probability of hitting the boundary. So it has, say, a probability P less than 1 of even crossing this line. And now once it does cross this line, again, it has a good chance of hitting one of these two sides before it continues. And so it has to sort of jump a second hurdle and then a third hurdle. And so it has to overcome on the order of R different hurdles before it can even reach A. So this harmonic measure, just by that kind of intuitive argument, is less than or equal to some probability less than 1 raised to the power of R. And that shows in particular that this probability goes to 0 exponentially fast in R. Now, of course, in the case at hand, we could actually compute this probability. But the point is that by being able to imagine the process that of Brownian motion that's necessary to reach A, we can get a quick and intuitive feeling for what this harmonic measure should be. Okay, now there's a second conformal invariant I want to mention that can be reinterpreted in terms of Brownian motion, which is our friendly equilibrium measure. This came up when we were studying capacity. It has a fairly complicated definition in terms of the Green's function for a region, but it's attached to any compact set K in the plane. So imagine you have like a tree with fruit. Just for simplicity, I'll make my set connected. And what we constructed was a natural way to put a measure mu. We constructed in a natural way a probability measure mu on K. And in fact, it lived on the boundary of K. Well, now I can tell you what that probability measure is. This measure mu applied to any set E is the probability that a Brownian path started at the point at infinity, it belongs to E when it first reaches K. So tau is the time it first reaches K. And this Brownian path starts at the point at infinity. And so it's very far away and it comes wandering in like this. And then it finally touches K. And we record where it first reaches it. And we do this over many different Brownian paths to get samples. And then the harmonic measure, or the capacity of the equilibrium measure of a set E, is the probability that this random path lands in our set E. Now, you might be a little dubious about the idea of Brownian motion starting at the point at infinity. But remember, Brownian motion up to a time change is invariant under conformal maps. So we could always apply the map z goes to 1 over z and make this Brownian motion starting at 0, which is perfectly well defined. And the measure we're constructing does not depend on the time parameterization of the infinity. It only depends on what the paths are. All we have to know is for each Brownian path that ends at K, what's the probability of that path actually occurring? And so it's insensitive to time change, and therefore it leads to the definition of this equilibrium measure. And so what you can gather from this intuitively is the following fact, which is well known to electricians, or I should say electrical engineers or people who work with conductors, is if you have a set K, which is very spiky, the equilibrium measure tends to be concentrated near the tips. This is also why it's good to put a lightning rod on top of your house. The equilibrium measure, if there's some static electrical charge on your house, it'll flow up and be concentrated near the tip of your lightning rod. And then the lightning will tend to strike there. But the intuitive reason for this is very similar to the intuitive reason that A has very small harmonic measure here. Namely, when a Brownian path comes down to hit this set, it has a very high probability of landing near one of these tips. And it's hard for it to get down into one of these triple points of the set because it has to not wind around very much en route to that point. So in fact, this equilibrium measure is concentrated on the tips of the set. And even if this set has positive Lebesgue measure or is fractal, it can be shown, this is a big theorem, that mu lives on a set of Hausdorff dimension 1. But the main point I want to emphasize is that with this tool of Brownian motion in hand, you have a very good intuition for what the equilibrium measure is.
How do we know that, or at least for what class of compact sets K is it a non-zero probability that we hit?
Great question. Okay, so what property does K have to have for this to even be defined? For example, we've seen that if you take a single point, the probability of Brownian motion hitting that point is 0. So there is no equilibrium measure on a point. But also, when we defined equilibrium measure in general, we didn't define it for all compact sets K. Does anybody remember, other than Henry maybe, is raising the question, what compact sets K have a well-defined equilibrium measure? What property does K need to have? I'll give you a clue. It was in the section on capacity.
I thought it was locally connected.
So certainly a non-trivial continuum has positive capacity, but actually there are quite thin sets that have positive capacity. Oops, sorry, I gave it away. Okay, so the criterion for the existence of equilibrium measure is that the set should have positive capacity. So equilibrium measure was only defined on sets of positive capacity. Remember, a set had to have a Green's function, and not every set has a Green's function. Having a Green's function is equivalent to the transfinite diameter of the set being positive, or one of the many other equivalent definitions of capacity that we studied being positive. So one thing that you did prove on the homework was that the capacity of the standard middle thirds Cantor set is positive. And therefore, remarkably, there is an equilibrium measure on the middle thirds Cantor set. There are very thin Cantor sets that have capacity 0, but the standard one, which I'll just draw like this, you have to intersect these sets, getting smaller and smaller, but the standard middle thirds Cantor set has positive capacity. And as a consequence, Brownian motion has a definite chance of hitting the middle thirds Cantor set, even though it has a measure 0, even though it has linear measure 0, even though it's not a connected set. But it has 0 chance of hitting a point, an isolated point, and there are very thin Cantor sets, which it has 0 probability of hitting. So the exact criterion for Brownian motion to hit a set is that the set has positive capacity. And let me just, as like a little digression, explain why the middle thirds Cantor set is visible to Brownian motion. because it looks very thin. How could Brownian motion possibly hit this when it won't hit single points? What's the difference? And the difference is this. One way to think of the middle thirds Cantor set is you have two disks enclosing the first third and the second third. And then within this, you have two smaller disks enclosing the intervals of length and ninth. And then you have two disks inside of this, and so on. And now you might ask, what does this look like in the hyperbolic metric? And what it looks like is a self-similar surface. It's like the first region here between the big disk and the two smaller disks looks like a pair of pants, or maybe even I'll put a single disk here. So this really big region A looks like a pair of pants. And then inside of this, we have A1 and A2, but they look the same. And then below that, we have A3 and A4, they also look the same. So from the point of view of the hyperbolic metric, the complement of the Cantor set looks combinatorially very much like a tree, like a bifurcating tree like this. And all of the pieces look similar to one another because the Cantor set is self-similar. Okay, now what does Brownian motion do? It comes wandering down here and it does not care what metric you use. We're only interested in the paths, not the speed. So you can think of Brownian motion investigating this Riemann surface using this metric. And what happens is it wanders down the tree, and each time it reaches a vertex, it has a 1/3 probability of backtracking and a 2/3 probability of going deeper into the tree. So it's like a Brownian motion with drift. And because it's biased to go deeper into the tree, it has probability 1 of converging to an endpoint of the tree, which means exactly that it hits the Cantor set. Okay, so there's a lot to say about Brownian motion. Let me just say a corollary of this picture and of the fact that harmonic measure exists there is that every Z in the 1/3 Cantor set, K, is a regular point. So this shows that the criterion for regularity is actually, it's very weak. You don't have to have this business about a triangle touching points or anything like that. Even this totally connected set K has the property that if you start a Brownian path at a point in K, you have probability 1 of hitting the Cantor set in arbitrarily small time. Okay, so that's concludes my discussion of harmonic functions, conformal mappings, harmonic functions as limits of discrete functions, and harmonic functions conceived in terms of this continuous process Brownian motion. And I want to turn to the last topic of the course, which is percolation. But any questions at this juncture? This is kind of a natural breaking point.
So we know that every point on the Cantor set is regular. So I guess like the obvious thing is true that like if you want to solve if you want to given any function on the Cantor set, you can have a harmonic extension.
Any continuous, so
it has to be continuous on the Cantor set.
That's right. So in other words, you can take a function, for example, that's equal to 1 on the Cantor set, and then you put, say, the disk of radius 2 around the Cantor set, and then get 0 there. And there is a harmonic function that peaks at the Cantor set and is 0 on the boundaries, harmonic in between. And that's a big difference from the isolated point. If you tried to make a harmonic function that was 1 here and 0 here, it just wouldn't work. It would come out being identically 0. So notice that the formula we wrote for the solution to the Dirichlet problem, it works for any continuous function on the circle. So every continuous function determines a harmonic function. It's just that harmonic function might not meet up with the original boundary values. It only meets up at the regular boundary points. Other questions, comments before we proceed? Okay, so I want to take a little breather and use this to do this segue. Let's look at some pictures. So there's lots of pictures on the course webpage that are relevant to what we're discussing right now. Let me start with this picture of the Julia set. So there's now a sort of probabilistic interpretation of these level sets in the Julia set, these level sets of the Green's function. And what these are showing us is Brownian motion is trying to come down and hit the Julia set, which is this fractal black set here. And these black loops are sort of how far it's gotten after a certain time. And what you can see is it's very close to hitting some of the tips of the Julia set, and it's very far from these regions that are deep inside. And that reflects this property I was mentioning before, that the equilibrium measure, the electrical charge, tends to concentrate at the tips of the Julia set. And in fact, it's quite hard to draw a good picture of the Julia set by the most naive algorithms because of this. What you tend to get is a picture that emphasizes the tips and doesn't show these deep fjords, as they're called, because Brownian motion kind of refuses to go very deep into the fjords. Okay, so that's one illustration. The next thing I want to show you is a graph of Brownian motion on the interval from 0 to 1. So remember, we constructed this kind of Brownian motion using Levy's method. And here's what the graph actually looks like. So you can see this is just the function b of t going from 0 to 1 for a typical point. I mean, it's a random process, so I took a sample. This is what a typical Brownian path looks like. And you can see it's very steep. That's because it has this 1/2 Helder modulus of continuity. In fact, it's nowhere differentiable. And it's a really good exercise, if you're at all interested in Brownian motion, to write a short script, say a Mathematica program, that draws Brownian motion for on the interval 0, 1, like I've done here. All you do is you take a random walk with 1,000 steps and rescale it appropriately. You get one of these graphs. And what you find as you run this script, which has to use a random number generator to create the output, is that every path you look at is different, but all the paths look the same. And it's really, you can actually recognize Brownian motion very quickly once you've looked at several samples of it. So it only takes about 10 lines in Mathematica to write a program to draw this picture. And it's really useful to examine many of them to get a feel for what Brownian motion looks like. Now, Brownian motion is supposed to arise as a scaling limit of random walks. And this movie, which has been up since the course started, shows that. So I stole this from the web, but it just shows a random walk being viewed from farther and farther away. So we start out with this discrete process of 1,000-step random walk. And as I discussed in Donskoy's theorem, we draw straight lines between the steps. So we get a continuous piecewise linear function. And as you look at it from farther and farther away, we scaled in the right way. It looks more and more like the graph of honest Brownian motion. So Brownian motion is very accessible in the sense that you can find very robust approximations to it without any difficulty. Now, what about Brownian motion in the plane? So I mentioned that it does this spiraling business. It's hard to draw Brownian motion in the plane because you have one time parameter and two space parameters. So I'm just going to draw the image of a Brownian path starting at the origin. And this is what it looks like. So you can see it just sort of looks like a big scribble. And it seems to actually fill in some regions solidly. But of course, it doesn't actually. There are these gaps here, these islands in the complement of Brownian motion. And in fact, the graph of Brownian motion is, the image here is the continuous image of the interval. So it's a compact set. And this compact set is nowhere dense. It doesn't fill in any of these regions. There's holes. It's just some of the holes are very small. But if you look at what's happening near the origin, you can kind of get a feel for this fact that this Brownian path is really reluctant to say stay in one quadrant. It wants to spiral around the origin and spiral around it infinitely often. So if we were to zoom in at the origin, it would continue to occupy all four quadrants, which is a particular case of this statement we made that a Brownian path is going to hit any given triangle infinitely often in arbitrarily small time. On the other hand, these islands, they also suggest the true fact that the graph of Brownian motion, the image has measure 0. And so your chance of actually hitting another given point, for example, this point 100, looks like it might have been hit, but in fact, it has 0 probability that we actually hit there. If we were to zoom in, 100 would in fact be enclosed in an island like one of these other things, or possibly being outside of the image altogether. Okay, now here is a rendering of the construction of Brownian motion we did last time. So again, this is very fun to try to do yourself. It's a short code once you've decided how to write it. But the construction here was, we want a Brownian path starting at 0. So we start at 0 and then we pick at random the value at 1 according to the Gaussian distribution. Then we draw this blue straight line. That's the first step in Paul Levy's construction. And then we pop out a triangle at time 1/2. The triangle happens to go below the real axis here. We could have gone above with equal probability. Then we have our second approximation, is this triangular path that passes through this point and then this vertex at 1. And then we pop out smaller triangles and smaller triangles and smaller triangles, all of which are drawn here. And in the limit, we get this jagged Brownian path, which is in fact the first path I showed you at the beginning of this little tour of the images. Okay, so I won't explain this image, but there's a discussion that I haven't had time to give of why Brownian motion is conformally invariant. And I'll just leave you to look at that in the text, that it involves something called Ito's formula. And this graph is a very nice introduction to Ito's formula. Okay, great. So I want to now change gears one last time and talk about a different kind of continuum limit, which, like Brownian motion, like discrete harmonic functions, turns out to be conformally invariant. But the conformal invariance of this limit is much more delicate, and it was a major breakthrough. It was only done about 20 years ago. And it's what I introduced the course with. So let me just remind you how we started. So we discussed the game of Hex, which is played on a finite grid with the sort of hexagonal or regular triangular symmetry. And the idea was players choose sites in this table. The blue player gets to color them blue, the red player gets to color them red, and they try to make a connection from one side to the other. The blue player connecting the blue sides, the red player connecting the red sides. And the point of this picture is that one player or the other always wins. If there's no blue connection at the end, then there has to be a red connection. Here there's a blue connection going from one side to the other. It's pivotal around this light blue square in the middle. and then there was the idea of what happens if players play hex at random. So there's no strategy, and the squares are just colored black or white with probability a half. Then maybe there's a connection between the black edges here, or a connection between the green edges. So which is it? Well, I think there's a white channel here which connects the green edges. So actually, green has won if it's playing white, so to speak, in this particular instance. But we can ask, what's the probability that there's a connection between the green edges, or what's the probability that there's a connection between the black edges? And the amazing answer is that that probability is a conformal invariant of the region where you're playing hex. That is, as you take the mesh smaller and smaller, the answer you get for the region that's drawn on the left is the same as the answer you get for the region that's drawn on the right, if these two are conformally equivalent. And we know that any Jordan domain with 4 mark points is isomorphic to a rectangle. So the answer you get for a given irregular region is the same as the answer you get for the corresponding rectangle. And you might say, oh, that's obvious, just apply the conformal map. But the conformal map greatly distorts the hexagonal tiling we're using in the left region. And we don't use that distorted tiling in the right region. We use the ordinary tiling. And the amazing fact is that not only does this probability exist, that's already highly non-trivial, but that it only depends on the conformal geometry of the region in question. So that's the phenomena that we're going to investigate. Okay, so let me start the discussion of this final topic by stating Smirnoff's theorem. And again, there's a whole chapter in the course notes now that describes in more detail what I'm going to do this class and the last class. So I encourage you to read that, because some things I'll have to do a little bit rapidly. And I also have a reference to Smirnoff's original paper, which is also very short and a pleasure to read. Okay, so let me start with the statement of Smirnoff's theorem, and then I'll tell you the story behind it. So we have this idea. As conformal geometers, we're very familiar with the idea of a quadrilateral. A quadrilateral, Q, is just a Jordan domain with some marked boundary points. And the points are marked in cyclic order. And we often use this marking to distinguish two sides of the quadrilateral. So this side here, we might call alpha, and this side here, alpha prime. Those are the A sides. Thank you. And of course, a basic theorem is that there's a conformal map, a Riemann mapping, that sends Q to an ordinary rectangle of dimensions A and B, sending alpha and alpha prime to the corresponding sides of this standard rectangle. So there's only one invariant of a quadrilateral up to conformal change of coordinates, which is the modulus. And the modulus of Q is defined as A over B. And this is the standard rectangle arc of AB. Okay, so now what we have to imagine is doing percolation in this region, which means we play the game of hex on a very, very fine grid and take the limit. So I'll make that much more precise in a moment, but I've indicated in the pictures what that means. And then Smirnoff's theorem is the following. The probability P of Q that a critical percolation cluster joins the A sides of Q exists. In other words, that limit, as we make the mesh smaller and smaller, converges and depends only on the conformal geometry of Q, and therefore only on one number on the modulus of Q, which is this fraction A over B. Okay, so what's being posited here is, from an intuitive point of view, and in a point of view that I think physicists would promulgate, is that in fact percolation itself should, in the limit, define some sort of continua, random complicated sets inside of this region Q. And when we choose one of these sets at random, the probability that it joins these two sides of the quadrilateral is a conformal invariant. In fact, the set itself should be a conformal invariant in the same way that Brownian paths are conformally invariant. So we're not going to prove that, although that can be done. That is, one can construct a random choice of sets inside of Q in such a way that it's conformally invariant. What we're going to prove is not that quite that strong, but this very suggestive theorem, namely that an observable of that phenomena, the probability that there's a percolation cluster that joins the A sides, that this exists, and it's a conformal invariant. Okay, so maybe first, let's talk about percolation per se. So what is the study of percolation? So percolation is about the following fairly general problem. So let's let G be a connected graph, and V of G are its vertices. And then I want to pick inside of here S. This graph should have infinitely many vertices. And I want to pick inside of here S, but it doesn't have to, I should say, generally infinite. S should be a random set of vertices of density. Now, what does that mean formally? It just means that the probability that a given vertex Vi is in S is equal to P, and these events that Vi is in S, Vj is in S, etc., these are independent events. So in other words, we take a biased coin that has probability P of coming up heads, we flip it at every site in the graph, and then we choose for our set S the vertices where that coin came up heads. Okay, now, we've only used the vertices of the graph. How are we going to use the edges? We use the edges to define connected sets. So a cluster, S naught contained in S, is a maximal edge connected set. So once we've chosen this set, we can pick a particular vertex in the set and see if its neighbors are in the set. If so, we adjoin those to the cluster. We keep doing that until we can't go any farther. We've included every site that can be connected to our original one by a path, all of whose vertices are in S, and that's the cluster containing the given base point. So the whole graph breaks up into many clusters, although there will be some vertices that aren't included in any cluster because they weren't chosen. And now before one gets to these very fine details about crossing probabilities, there's a much more fundamental and simple question you can ask. What is the probability that there exists an infinite cluster? And that is really that was the main question in percolation for many decades. So the percolation problem is does S have an infinite cluster? Now let me clarify something. For me, a graph at every vertex, it has at most finitely many edges. It has this mild tameness property. Even if the graph is infinite, there's only finitely many edges at each vertex. So the first observation is the event S contains an infinite cluster is a tail event. And so its probability is equal to 0 or 1 by Kolmogorov's theorem. Why is it a tail event? To say it's a tail event means that if you have an infinite cluster and you change the values, the elements of S, if you change finitely many elements of S, it doesn't affect the outcome. So it only depends on the values, the shape of the set S outside of arbitrarily large bounded sets inside of your graph G. So why is that the case? So here's our graph G, and we take some large bounded set B, and now suppose we have an infinite cluster. So this is our infinite cluster. There's other parts of S that are not included in the cluster. And now suppose we delete this large bounded set. I claim we still have an infinite cluster, because when we delete this set, S naught breaks up into at most a finite number of connected subsets, because we've removed only finitely many vertices. And so when we do that, we've taken an infinite set and we've written it as the union of finitely many sets. So one of them has to still be infinite. So the cluster might get smaller, it might separate into more pieces, but it's still infinite. And therefore, the choice of whether or not these vertices are in the original set S or not doesn't affect the existence of an infinite cluster. So this probability is 0 or 1. So this probability, of course, also depends on this critical parameter P, the density of the cluster. So if we graph the probability of an infinite cluster as a function of P, what happens? Well, certainly when P is 1, if the graph is infinite, then we have an infinite cluster. And when P is 0, the set is empty, so we don't have an infinite cluster. And so what happens is there's some point where it jumps from 0 to 1. And that point is called the critical probability for percolation on the given graph. Of course, it depends on the graph in question, and it might be 0 or 1. Also, we don't know, even though we've defined PC, we don't know whether the probability of an infinite cluster is 0 or 1 at that particular site. But anyway, this was the main question that was studied for many decades. Just what happens? What can you say about this critical probability, even for very simple graphs? Now, physicists were able to make a ton of predictions about percolation because they're not held back by the necessity of proving theorems. So for them, there were certain obvious values of what should happen here. And then they were also able to discuss the fine structure of the percolation clusters for values of P close to PC. And then they predicted, based on all sorts of intuitions, including sort of conformal field theories, that the structure of clusters at this critical probability should be conformally invariant. There should be sort of long-range correlations, and sort of the scale of the lattice should become irrelevant when you're at this phase transition. So we are going to study in the context of Smirnoff's theorem, one graph. And our graph is going to have as vertices almost the square lattice, but it's not going to be the square lattice, it's going to be the triangular lattice. So here omega is a cube root of unity, it's the one in the upper half plane. So it's -1/2 plus I times the square root of 3/2. And we're going to study this lattice. So it's generated by 1 and by omega. This points in this direction. This is omega. And this is omega plus 1. And we connect two vertices in this graph when they're distance 1 apart, just like we would do in the case of the Gaussian integers or the square lattice, which we used when we studied discrete harmonic functions. Okay, so this is my graph. The vertices of the graph are the Eisenstein integers, if you like, and the edges, we have an edge from x1 to x2 if and only if the difference between x1 and x2 is equal to 1. So this is a graph of degree 6. There's 6 edges attached to every vertex. Now, we could also have considered the square lattice, whose vertices are z adjoint I. So I'm going to give these names. I'm going to call this just the square lattice, and I'm going to call this the triangular lattice. Now, what's the relation, by the way, to the hexagonal tiling, which we used when we drew the pictures for the Game of Hex? Well, we're going to be doing percolation on these sets, and so we'll be choosing some collection of vertices at random, and it's kind of hard to see vertices. So what people often do is they associate to each vertex the face of the dual self-complex. So this graph gives a triangulation of the plane, and there's a dual subdivision of the plane where each vertex becomes a face and each face becomes a vertex. And sorry, I'm drawing this wrong. I should put a vertex in the center of each face here. There we go. So there's a way to associate a cell division into hexagons, and it's easier to see blue hexagons than it is to see these little blue vertices. But we will, in fact, be doing percolation on the triangular lattice because it's the vertices of this lattice that we'll be using to construct our random set. Okay, so here's a theorem which was surprisingly difficult to prove, which is that PC equals 1/2 for both the square and triangular lattices. So we know what critical percolation means on the triangular lattice. It means that we choose each vertex by flipping a fair coin. So in other words, we choose half the vertices, and at that point, there may or may not be an infinite cluster. But what we're interested in is what are the behavior of clusters when we choose the vertices with equal probability. Okay. By the way, there's an intuitive argument that PC should have to be 1/2, because it seems like either the set you that let's call these blue points the ones that are in our set S. Either you have a blue cluster, or if you draw the complementary points yellow, this is Smirnoff's terminology, either you should have an infinite blue cluster or an infinite yellow cluster, right? So you should have one or the other. And so somehow by symmetry, you would expect that when the critical probability has to be a half. But that's not right. You see, there might be a whole range of probabilities where neither the blue or the yellow have an infinite cluster. The blue interrupts the yellow and the yellow interrupts the blue over and over again. And in fact, we will later see that at this critical probability, there is no infinite cluster. In fact, there's no infinite cluster when we take P to be equal to half. Okay, so now let me turn back to the statement of Smirnoff's theorem. So what's the definition of this crossing probability of a quadrilateral? It's very simple. So for each h greater than 0, we do the usual thing. We let QH be Q intersect H times the triangular lattice. So we take a fine approximation to our quadrilateral Q by equilateral triangles. And then we take the induced subgraph of G, finite subgraph of G, that is, we just include the edges that join points in this finite set. And then we label parts of boundary Q, H, as A sides if they approximate the A sides of Q, as we showed in the pictures that I drew. And then we have P of QH is now completely rigorously defined because we have a finite graph. We have two parts of its boundary. We can talk about clusters without any difficulty. And then this is just the probability that there exists a cluster as not joining the A sides of QH. And then, of course, P of Q is defined to be the limit as H goes to 0 of P of QH, assuming that this limit exists. Okay, now, why are we doing this at the critical case? So here's a remark that is not too hard to justify. So remember, in the background, there's this density P. And in Smirnoff's theorem, we're taking P equal to PC. But we could carry out this definition for any particular value of the density of the cluster. And in fact, if we did that, we would get P of Q is equal to 0 if P is less than the critical probability, and it's equal to 1 if P is greater than the critical probability. So there's no interesting observable if you're not at the critical probability. Once you have probability 1 of having an infinite cluster, everything gets crossed. In fact, Q just kind of looks black. Even though the density is small, the size of the clusters is big. And if you're below the critical probability, the clusters are almost invisible. So this indicates there's a sort of very sharp phase transition when you pass the critical probability. And I want to illustrate that with a little simulation I did that also gives you an idea of what these critical probabilities are about. So here's an experiment is you make a fairly large finite grid, and you pick a point in the center. This is a piece of the triangular lattice. You pick a point in the middle, and then you start randomly adding points to S. And you might eventually add a point that's close to this point, so then you join it by an edge. And you start adding more points, and then maybe you actually add this too. And you keep doing this, and what happens is, provided the density of S remains less than a half, this cluster in the middle is rather small. But just as you cross 50% density, suddenly all sorts of incipient clusters get joined to it, and it fills up most of the quadrilateral all at once, just as you pass P as a half. So again, this is something that's fun to program and observe over and over again. But let me just share the outcome of that experiment, which is also on the webpage for the course. So that's this picture of percolation clusters. So I started out with a rhombus, which was completely yellow, and then started slowly turning sites blue at random. And the exact center of the rhombus is colored green. And then whenever a blue site is connected to that central green point, I also color it green. So in the first frame, this reads like you're reading text from right to left and top to bottom. At this fairly low density, that cluster just consists of 2 points. And then as the density increases, you see you're starting to get other blue clusters, but they're not connected to this central one. The central one gets a little bit bigger, and then a little bit bigger here. And you can still see that the orange is, the yellow is dominating the picture, a little bit bigger here, and then suddenly, bam, the cluster explodes. A bunch of these other smaller clusters all join together, and you get this huge green structure in the middle of the picture, and then at a slightly higher probability, it just completely dominates the connectivity of the chosen set S. Okay, so this is kind of the birth of the infinite cluster approximated at a finite scale. Okay. So enough of the generalities about percolation. Let me turn to another question that was asked to me recently. Does percolation depend on the choice of lattice? Why are we using the Eisenstein integers rather than the square lattice? Well, in fact, Smirnoff's theorem has only been proved for the triangular lattice. It is an open problem for the square lattice. And that's very contrary to popular belief among experts and belief supported by physical arguments that the limit of percolation should be very robust. It's a kind of, there's normalization ideas that say it shouldn't have anything to do with the original lattice. Any lattice or any reasonable graph should in the scaling limit have the same limiting conformally invariant process. But in fact, it's only been proved for the triangular lattice. Why only the triangular lattice? That's one question one could ask. And there's a closely related question, which is, I said that the crossing probability, P of Q, and this is now at the critical probability a half, the crossing probability, this conformally invariant thing, is just a function of the modulus of Q. So what function is it? Well, I won't write down the formula, but there's something called Cardy's formula. Is a prediction for F. This was made before Smirnoff's theorem, predicts that F of the modulus is some complicated thing involving a hypergeometric function. So the formula was pretty complicated, and that made it look like the solution of the problem would be extremely complex. However, there was an observation made by Leonard Carlson that I think was really the first breakthrough in the subject and that underlies Smirnoff's proof, and which explains why somehow the triangular lattice is more important than every other lattice in this discussion. So Carlson considered the following question. Here's a particular Q. I start with an equilateral triangle. After all, every region is supposed to have a crossing probability. So why not this region? And then I only have 3 distinguished vertices so far. So I'm going to choose a 4th vertex here, which is along the edge from A to C. And now I'm going to turn this into a quadrilateral by calling these 2 edges the A sides. And I ask, what's the probability that there's a percolation cluster that joins these 2 sides? Well, Cardy's formula predicts what that probability should be. And Carlson observed that if you translate that into the crossing probability for this quadrilateral, that the crossing probability is the length of AX divided by the length of AC. In other words, it's a linear function of this distance. As X approaches C, the probability of a crossing goes to 1, and it's just proportional to the length of this edge. So indeed, in what's hidden here, the reason this formula is so complicated is that the conformal map that sends this triangle to a rectangle is very complicated. But if we don't bother sending it to a rectangle, if we leave it as an equilateral triangle, then the formula becomes very simple. Okay, so now I can tell you, at least in brief, what Smirnoff's big breakthrough was, or what the real theorem is that he proved. So one of the theorems that he proved has to do with this equilateral triangle. And his idea was to consider this point X not lying in the edge of the triangle, but in the interior of the triangle. And now, rather than asking if there's a percolation cluster that joins this edge to this edge, he just asks, is there a percolation cluster that separates the point Z from this edge from A to B? And so another version of Smirnoff's theorem, or an instance of Smirnoff's theorem, is that the probability that a cluster separates Z from the edge AB is equal to exactly the, well, let me pretend that this is the real axis here, so that A and B lie on the real axis, is exactly the imaginary part of Z divided by the imaginary part of C. In other words, it's the height of Z above the real axis. So this was a key insight, was that rather than trying to compute these crossing probabilities, one should extend this idea to points that are in the interior of the region Q. And you can see that if as Z approaches X, this probability here tends to the probability that there's a crossing from this edge to this edge. And of course, this quantity, the ratio of the height of Z to the height at the top of the triangle, is the same as the ratio of this length to this length. So this theorem of Smirnoff implies that Carlson's formula and Cardy's formula are correct when the region happens to be a triangle. Okay, now the one thing that's missing here is conformal invariance. I discussed how this is done in the specific instance of an equilateral triangle, but to prove the deep result that percolation is conformally invariant, we need to have a conformally invariant notion of an equilateral triangle. And that's very simple because we know what quadrilaterals are. So there's a generalization of a quadrilateral, which is even simpler, which is a conformal triangle. So a conformal triangle consists of a Jordan domain with 3 points marked on its boundary. So T is a Jordan domain, and Ti are in the boundary of T, and they should be cyclically ordered, as you might imagine, T0, T1, and T2. And then the key observation here is that this quantity, imaginary Z over imaginary C, this is harmonic. And it turns out that there are analogous harmonic functions that you can define in any conformal triangle. So associated to this triangle, in a way I'll specify next time, there are 3 functions, B0, B1, and B2, which I call the barycentric coordinates on the triangle. They're harmonic. And then Smirnoff's theorem can be reformulated by saying that the probability B0 of Z, this is the probability of a cluster separating, or let me call it BI of Z, separating Z from edge I of the triangle is equal to the ith barycentric coordinate. So the 0 edge of the triangle is here. This is called side 0 because it's opposite the vertex labeled T0. And B0 is the probability that this point Z is separated from this edge by a cluster, which means that we have this picture. And in fact, the key to the proof is the following insight. It is nearly impossible to prove directly that this function is harmonic if you consider only this function by itself, the one for T0. But if you consider all 3 functions, the separation properties for this edge, and this edge, those 3 probabilities fit together to give a package from which you can build not just a harmonic function, but a holomorphic function. And by showing that you get a holomorphic function in the limit, you'll get number 1, conformal invariance, and number 2, you'll get the exact value for what this crossing probability should be. So in many ways, the discussion will mimic our proof that discrete harmonic functions tend to honest harmonic functions in the limit. We'll be trying to prove that some probability defined discretely has a beautiful and simple limit in any conformal triangle. Okay, so I'll finish sketching the proof of Smirnoff's theorem next time as our final instance of conformal invariance and limits of discrete probabilistic processes. Okay.